This is sample 8-6. How high does it go? I'm on page 350 here. Now, when we were close to Earth, we could really simplify this problem, but this is going to deal with what happens when you get far enough away from Earth's surface that you can't just use MGH for gravitational potential energy. And it's a little messy, I admit, but it's not difficult. It's absolutely doable. So we have a rocket with a mass of 2.4 times 10 to the 4th kilograms. We're going to launch it straight up from Earth's surface, and we're going to give it an initial kinetic energy. Then the engine's going to shut off, and we're going to find out to what maximum height above Earth's surface will the rocket rise. So let's take just an idea here. Since we can ignore air resistance, we are going to our energy conservation statement is going to be that total mechanical energy is constant. So, is it worth writing mechanical energy initial equals mechanical energy final? Maybe, because we've got only conservative forces. All right, so at least we're very clear what we're doing and why. So we have initial plus initial for kinetic and gravitational potential energy equals final kinetic energy plus the final gravitational potential energy. There's no spring in this problem, so we don't need to indicate that. So formulas we have for energy are, well, at least kinetic energy didn't get any more confusing or complicated. 1/2 mv squared. For our gravitational potential energy, we have negative, remember, capital G. We've got the mass of the Earth and the mass of the rocket, so I'll be clear there. R is the distance between them. So let's write down our data here. The mass of the rocket is 2.4 times 10 to the 4th kilograms. Earth's mass, and you would be given this these sorts of astronomical data on a test, unless it's on your formula sheet, so don't forget to look at your formula sheet. The radius of the Earth is also given, and be so careful about the units, because oftentimes the radius of the Earth is given in kilometers because it's 6,370, and that's sort of a manageable number. That's fine. Just make sure that you convert to meters when you need to do that. If you're just adding, then it's not a problem. But if you're going to put these into formulas, make sure you're in meters. Okay, so here's our data, and you can come back to that if you need to as the problem goes along. So we're going to say initial conditions here at launch, okay? Our kinetic energy is 1/2 times the mass of the rocket, right? Not the mass of the Earth. And then we're told that it's given an initial speed of 9 kilometers per second, all right? Be careful there, 9,000 meters per second. That quantity is squared, so once pause to plug in chug, and you get 9.72 times 10 to the 11th joules. So that's its kinetic energy at launch. So yes, it does take some vertical space to get to that speed, but the problem makes it pretty clear that that distance is negligible compared with the distance that the rocket's going to rise. So we're going to say initial conditions are on Earth's surface, but also it's given a speed, and that's fine. That's our initial gravitational our initial kinetic energy. Our initial gravitational potential energy, then we're going to use negative G times mass of the Earth times mass of the rocket divided by the radius of Earth. Because remember, we're considering this to start from Earth's surface, so we need to use the radius of the Earth. I really encourage you to pause this, do your own plugging and chugging, make sure you have the right units, make sure you have the right meters, kilometers for the radius, okay? Your answer then is negative 1.50 times 10 to the 12th joules. All right, so those are our initial energies. So let's say our initial energy is Ki plus UGI. That's a negative 5.28 times 10 to the 11th joules. And since mechanical energy is being conserved, that's also our final energy, right? And don't worry about the fact that it's negative. Remember, all we care about are changes, okay? All we care about are changes in energy. So let's go to the end of the problem then, the final conditions. When we say how far does it go before it stops, that's a pretty big indicator that our final kinetic energy is 0, which simplifies this quite a bit. Our final gravitational potential energy is then equal to this 5.28 times 10 to the 11th joules. Right now, I'm going to go on to the next page because I've run out of room. So I'm going to copy that number. Equals, oops, sorry for the stray marks here. And that's negative G, mass of the Earth, mass of the rocket, over R. And there's a couple ways to look at this. Remember, this R is going to include Earth's radius, so we'll come back. Again, please pause, crunch the numbers for yourself, and when you come back, you'll find that the rocket is 1.81 times 10 to the 7th meters. Now, remember, this is from center of Earth. And given a question like this on an AP exam, you might just circle this answer and you're done, and they would be fine with that, so long as they are sure that you're clear that this is from the center of the Earth, not from Earth's surface. So I think if I wanted to cover all of my bases, how high is this above the ground? Yeah, I would say, well, that's the R that that's the R that I just got minus Earth's radius. So 1.81 times 10 to the 7th meters. Subtract out Earth's radius, and we get 1.17 times 10 to the 7th meters from Earth's surface. So for me, certainly a problem like this, I don't care which radius you give, but be clear that you know where that radius is measured from. So like for me on a test, if you put this, 100%. If you put this, 100%. But if you just put the distance, then I need to know that you know what you're talking about. So anyways, that's about as complicated as it gets for gravitational potential energy. We've got one more problem, which is sample 8-7. But if you have questions on this one, let me know.